Tonight, we're going to take a journey alongside the two most distant human-made objects ever built, Voyager 1 and Voyager 2, and follow them all the way to the end of recognizable time. Right now, Voyager 1 is more than 25 billion kilometers from Earth, moving at 17 kilometers every second, and it has not slowed down in any meaningful way since it left. Because here's the thing, most people don't realize. These two spacecraft will almost outlast the Sun, the stars, and every planet in the galaxy. By the end of tonight, you're going to understand exactly why the Voyagers can never truly stop, what the universe looks like when they finally drift through it alone, and why two aluminum spacecraft launched in 1977 may be the last physical record that humanity ever existed. Before we dive in, if you love exploring the far reaches of the cosmos as much as we do, take a moment to like the video and subscribe. It's a small thing, but it helps this channel grow and reach more curious souls like you. Now, let's begin. There was a moment in 1964 that almost nobody outside of aerospace history remembers, and without it, none of what follows would be possible. A young graduate student named Gary Flandro was working at the Jet Propulsion Laboratory in Pasadena, California, when he sat down with a set of orbital calculations and noticed something that had been sitting in mathematics, unrecognized, for decades. In 1964, Flandro noted that an alignment of Jupiter, Saturn, Uranus, and Neptune would occur in the late 1970s, an arrangement that would enable a single spacecraft to visit all of the outer planets using gravity assists. That particular alignment occurs once every 175 years. Once every 175 years, the outer solar system arranges itself into a kind of cosmic staircase, and a spacecraft launched at precisely the right moment could step from one planet to the next, borrowing speed from each giant's gravitational field, accelerating outward faster than any rocket alone could manage. This led to the Voyager Grand Tour concept, utilizing the gravity assist technique to reduce the mission duration from 40 years to less than 10 years. Flandro's calculations revealed that Jupiter, Saturn, Uranus, and Neptune would align in such a way that one spacecraft could visit all four in a single mission if it launched by 1977. The craft would slingshot around each planet in succession, completing a grand tour in only 10 to 12 years, rather than the decades such a venture would otherwise require. The window would not come again in any of our lifetimes. It would not come again for another 175 years after 1977. So the question was not whether humanity would attempt it. The question was whether it could be done at all. Here is where the story becomes something larger than engineering. The Grand Tour, in its original conception, was ambitious enough to frighten the accountants. The mission gained momentum in 1966, when it was endorsed by NASA's Jet Propulsion Laboratory, but in December 1971, the Grand Tour mission was cancelled when funding was redirected to the Space Shuttle program. The full 4-spacecraft plan was gone. What remained was a scaled-down version, 2 probes instead of 4, with modest official ambitions and a secret understanding among the scientists that if everything worked, they might push the mission far beyond what the budget documents admitted. Due to budget constraints in the early 1970s, the ambitious plan was scaled back to 2 spacecraft, Voyager 1 and Voyager 2, launched in 1977, with primary objectives focused on Jupiter and Saturn. but later extended for Voyager 2 to include Uranus and Neptune. The two spacecraft were built on a tight schedule, tested, and readied at Cape Canaveral Air Force Station in Florida. Voyager 2 launched on August 20th, 1977. Voyager 1 followed on September 5th, 1977, 16 days apart. Two almost identical machines, each roughly the size and mass of a small car, loaded with instruments so sensitive they could detect magnetic field variations 1 billion kilometers from the source, powered by the slow, steady heat of decaying plutonium. They had no solar panels. Out past Mars, sunlight becomes too diffuse to be useful. Instead, each Voyager carried 3 radioisotope thermoelectric generators, devices that convert the heat of radioactive decay directly into electricity. Quiet, reliable, and finite. Voyager 2 actually launched first, on August 20th, 1977. But Voyager 1 took a shorter, faster route and a bigger gravitational kick. So it now travels roughly 2 kilometers per second quicker and sits billions of kilometers farther out. The two probes are heading in different directions, toward different constellations, through different regions of the galaxy's interstellar medium. They are siblings, not twins, in their trajectories. Stop here for a moment and feel the weight of that launch decision. The people who signed off on Voyager in 1972 were not thinking about 10 trillion years. They were thinking about 10 years. The political climate, the technical risks, the sheer audacity of sending a machine across the outer solar system, using the gravitational fields of planets as stepping stones. The engineers at the Jet Propulsion Laboratory in Pasadena designed computers that could process roughly 8,000 instructions per second, built instruments that would need to survive temperature swings from scorching heat near Jupiter to temperatures barely above absolute zero, and sent it all away from Earth on a trajectory calculated by hand and by early mainframes. Nobody in 1977 was thinking about where these machines would be in 10 trillion years. But that is exactly where we are going tonight. Before we trace the long arc of Voyager's future, it helps to understand what they actually became in the decade following launch, because those early years of science shaped everything that came after. They gave these machines their speed, they gave them their trajectories, and they gave humanity its first true understanding of the outer solar system. Voyager 1 reached closest approach with Jupiter on March 5th, 1979. Nothing had prepared the team for what the cameras showed. Jupiter, viewed from Earth, is a banded ball of gas, beautiful in its symmetry, regal in its scale. Up close, it is something else entirely. The bands are continent-wide storms, each one large enough to swallow the Earth multiple times. The Great Red Spot, observed through telescopes for centuries, turned out to be a storm system with internal wind speeds that defy ordinary description. The photographs alone would have justified the mission. But Jupiter's moons were the true revelation. Voyager 1 discovered a thin ring around Jupiter and 2 new Jovian moons, Tharp and Metis. And on the volcanic moon, Io, something no planetary scientist had predicted: active volcanoes, erupting in real time, visible in Voyager's images as bright plumes rising above the surface against the darkness of space. Io was not a dead, cratered relic. It was the most volcanically active body in the solar system. The tidal forces from Jupiter were kneading its interior like dough, generating enough heat to keep its surface in a state of permanent geological violence. At Saturn, Voyager 1 found 5 new moons and a new ring called the G-ring. Voyager 1 reached Saturn on November 12, 1980. The rings, already known to exist, turned out to be not 2 or 3 broad bands, but hundreds of thousands of individual ringlets, each composed of water ice particles ranging from grains the size of sand to boulders the size of houses, all orbiting in eerily precise formations that spoke of gravitational resonances still not fully understood. Saturn's largest moon, Titan, drew particular attention because it was known to have a substantial atmosphere. Voyager 1 was directed to fly close to Titan, close enough to image it in detail, and that decision changed everything. Because of the Titan flyby geometry, after Saturn, Voyager 1 headed north out of the ecliptic plane at a speed of about 3.5 astronomical units per year. Because of the specific requirements for the Titan flyby, the spacecraft was not directed to Uranus and Neptune. That trajectory, chosen for science, was also the trajectory that gave Voyager 1 its escape velocity from the solar system. The encounter with Saturn, approached at the right angle, flung the spacecraft northward and outward with a speed that the Sun's gravity at those distances would never fully overcome. Voyager 2 had a different destiny. Voyager 2 made its closest approach with Jupiter on July 9, 1979, and Saturn on August 25, 1981. Some sources list August 26th due to the exact UT crossover time. But unlike its sibling, Voyager 2 was directed onward. It became the only spacecraft in history to visit Uranus and Neptune. In January 1986, it flew past Uranus and discovered 10 new moons and 2 new rings around a planet that turned out to be tilted on its side, its axis of rotation nearly parallel to the plane of the solar system. Then, in August 1989, it reached Neptune, the outermost of the giant planets, a blue-white world of extraordinary storms. The largest of Neptune's storms, the Great Dark Spot, was comparable in size to Earth. Voyager 2 flew close enough to Neptune's largest moon, Triton, to image its nitrogen geysers, erupting not from volcanic heat, but from solar warming of a surface that sits at a temperature of roughly minus 235 degrees Celsius. Both spacecraft, through these encounters, accumulated velocity that would carry them outward forever. Take stock of where we are. Both Voyagers have completed their planetary science. Both have used the gravity of giant worlds to accelerate themselves to speeds their rockets alone could never have achieved. And both are now aimed at the interstellar void, carrying their instruments, their power supplies running low, and on each spacecraft side, a 12-inch gold-plated copper disc. The golden record deserves a moment of genuine attention because it is not merely a detail of the mission. It is the soul of what the Voyagers are once you extend the timeline far enough into the future. The contents of the record were selected for NASA by a committee chaired by Carl Sagan of Cornell University. The selection of content for the record took almost a year. The committee worked with a kind of impossible brief: produce a record of human civilization that would be intelligible to an intelligence that shares none of our assumptions. No common language, no common biology, no common context. What they assembled was, in some ways, a small miracle of intention. Sagan and his associates assembled 116 images and a variety of natural sounds, such as those made by surf, wind, thunder, and animals. To this, they added audio content to represent humanity, spoken greetings in 55 ancient and modern languages, and other human sounds like footsteps and laughter. Astronomer Frank Drake suggested a phonograph record, the hope being that a record would be more likely to survive the mission, and that alien life would be more likely to figure out how to use it to play humanity's message. The golden record was made of copper and plated in gold in order to satisfy the thermal and magnetic requirements of the Voyager probe. The cover of the record was electroplated with uranium-238, an isotope chosen not for decoration, but as a kind of geological clock. Any civilization sophisticated enough to find Voyager might also be sophisticated enough to measure how much of that uranium has decayed, and from its half-life, calculate how long the record has been traveling. It is a timestamp written in physics rather than language. The record's protective cover includes instructions for playing its contents, finding Earth in the cosmos, and dating how long it has been in space. Now consider what the record contains: greetings in 55 languages, the sound of rain on leaves, the first movement of Bach's Brandenburg Concerto No. 2, whale song, a human heartbeat, a mother's first words to a newborn child, diagrams of the human body, of DNA, of the mathematics that describes the physical world, images of Earth from space, images of forests and deserts and oceans and cities. Everything placed on that record was chosen because someone in 1977 believed it represented something worth preserving, something worth sending outward into time. The people who made those choices are gone now. Most of the people who launched these spacecraft are gone. The political world that funded the mission has transformed beyond recognition. And yet, the record travels on, attached to a machine that has never stopped, that has not slowed in any way a human body would perceive. That is right now, at this moment, crossing empty space at 17 kilometers every second. As of 2026, NASA's Voyager 1 is coasting through interstellar space more than 25 billion kilometers from Earth, roughly 167 astronomical units. It is still moving away at about 17 kilometers per second. Also, the one-way signal time is now more than 23 hours for Voyager 1 and roughly 19 hours for Voyager 2, making real-time control impossible. Voyager 2 is more than 137 astronomical units from Earth, also in interstellar space, heading roughly toward the constellation Pavo. Pavo, the peacock. Even the constellations the Voyagers aim toward carry a kind of accidental poetry. From the vantage point of Earth, Voyager 1 sits high above the plane of the planets, heading out through the northern constellation Ophiuchus. Ophiuchus, the serpent bearer, a constellation so large it intersects the ecliptic, but was excluded from the traditional zodiac. Neither spacecraft is heading toward any destination that was intentionally chosen. They are heading toward whatever the galaxy places in their path, which, given the scale of interstellar space, will almost certainly be nothing for an extraordinarily long time. Out in interstellar space, there is almost nothing to slow them down. There is no atmosphere and no meaningful drag, and the sun's gravity is now far too weak to rein them back. So while the spacecraft loses a whisper of speed to the sun's distant pull, for all practical purposes, Voyager 1 will keep this velocity essentially forever. There is a phrase worth sitting with: essentially forever. In the context of human experience, forever is a word we use loosely for things that last a generation or a century. In the context of these two spacecraft, forever means something that makes the age of the dinosaurs look like a Tuesday afternoon. It means timescales that will outlast the sun, outlast all the stars currently visible in tonight's sky, outlast the galaxies as we know them. The machines built in a factory in Pasadena, California, assembled by human hands, tested in a warehouse in the American Southwest, launched on a summer and autumn morning in 1977, will almost certainly persist in some form through the death of every star currently burning in the Milky Way. That is the territory we are entering tonight. And it begins, appropriately, with one last conversation. The Voyagers are still talking. Right now, as you listen to this, signals are traveling outward from the Jet Propulsion Laboratory's Deep Space Network through a 70-meter radio dish in Goldstone, California, or its counterpart in Madrid, Spain, or its partner in Canberra, Australia, riding on radio waves at the speed of light across more than 23 hours of empty space before they reach Voyager 1. The one-way signal time is over 22 hours for Voyager 1 and just under 20 hours for Voyager 2, making real-time control impossible. Commands must be planned days in advance. The conversation is winding down. In April 2026, engineers at NASA's Jet Propulsion Laboratory shut down an instrument aboard Voyager 1 to save power and keep humanity's first interstellar explorer going. Voyager 1 still has 2 science instruments operating, nearly 49 years into its mission. Years ago, Voyager scientists and engineers agreed on the order to shut off parts of the spacecraft to preserve power while ensuring the mission could continue to conduct its unique science. Voyager 1's electrical power comes from 3 radioisotope thermoelectric generators, fueled by plutonium-238. These RTGs produce heat from radioactive decay and convert it to electricity with no moving parts. The plutonium decays by about 0.78% per year, commonly rounded to roughly 0.8%. And Voyager's engineers have spent decades shutting off instruments and heaters one by one to stretch the remaining power budget. The arithmetic of that decay is pitiless. At 0.8% per year, the power available to the spacecraft falls below the threshold needed to operate any scientific instrument sometime in the late 2020s. Science operations are expected to end in the late 2020s as the plutonium-powered RTGs drop below the minimum power required to run any instruments. The spacecraft itself will continue on its trajectory forever, just silently. Silently. That is the word. Voyager 1 will continue outward at 17 kilometers per second. Voyager 2 will continue outward at 15 kilometers per second. Neither will stop. Neither will turn around. Neither will slow in any way that matters. But somewhere in the next few years, the last instrument will shut down. The last telemetry will cease. And these 2 machines will become what they have always been in their deepest nature. Not radio transmitters, not scientific platforms, not engineering achievements, but objects in motion. Objects in motion stay in motion. That is Newton's first law stated in 1687, and it applies to these spacecraft as absolutely as it applies to anything in the universe. There is nothing in the void between the stars to stop them. There is no friction, no resistance, no wall. They will keep going. They will keep going when the last human being has died. They will keep going when the sun has expanded into a red giant and consumed the orbit of Earth. They will keep going when the last star in the galaxy has burned out and the universe has grown cold and dark and vast beyond any reckoning. And what happens to them between now and then is one of the most beautiful and sobering stories that physics allows us to tell. That story starts with a journey through the Oort Cloud, and it begins now. Roughly 300 astronomical units from the Sun, the interstellar medium begins to feel genuinely alien. Voyager 1 has already crossed the heliopause, that boundary at roughly 121 astronomical units, where the Sun's outward flowing solar wind meets the incoming pressure of interstellar gas and yields. It crossed that boundary on August 25, 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018. They are both out there now in the region astronomers call the interstellar medium, the thin, cold, magnetized gas and dust that fills the space between stars. But here is something most descriptions of the Voyager mission quietly skip over. The heliopause is not the edge of the solar system. Not truly. The solar system has another boundary, one that makes the heliopause look close by comparison. It is a shell of frozen material called the Oort Cloud, a vast, roughly spherical distribution of comets and icy bodies that extends from roughly 2,000 astronomical units all the way out to perhaps 100,000 astronomical units from the Sun. To put that in terms that can sit in the body rather than simply in the mind, the heliopause, where both Voyagers have already crossed, sits at roughly 100 to 120 astronomical units. The Oort Cloud's inner edge begins at perhaps 2,000 astronomical units. Its outer edge may reach as far as 100,000 to 200,000 astronomical units, depending on the estimate. NASA's general range tops out around 100,000 astronomical units, while astronomer Seth Redfield of Wesleyan University, who has used the Hubble Space Telescope to study the Voyager's paths, places the boundary of the Sun's gravitational influence at roughly 200,000 astronomical units. Consider what this means. Voyager 1 has been traveling for nearly 49 years. It is more than 167 astronomical units from the Sun. It has crossed what most people call the boundary of the solar system, and it has barely begun to scratch the outer shell of the true solar system. The Oort Cloud is still thousands of astronomical units ahead. This is the first of the journey's great disorienting truths, and it arrives without fanfare. The solar system is not the size most of us picture. It is not the neat arrangement of 8 planets and a belt of asteroids that fits on a classroom poster. It is a structure whose outer reaches extend to distances that would take Voyager 1 roughly 300 years to cross at its current speed. 3 centuries of travel at 17 kilometers per second just to traverse the Oort Cloud. And the Oort Cloud itself is merely the outermost suburb of one ordinary star. At 17 kilometers per second, Voyager 1 covers about 3.5 astronomical units per year. The outer edge of the Oort Cloud sits perhaps 100,000 astronomical units away. So Voyager 1 will need somewhere between 14,000 and 28,000 years to traverse the full depth of the Oort Cloud, depending on which direction its path takes it, and which models of the cloud's outer boundary you trust. This is not a calculation anyone made with confidence in 1977. It is a calculation made possible by decades of improved understanding of the solar system's outer architecture. Here is what those 14,000 to 28,000 years look like in human terms. The last ice age ended roughly 11,700 years ago. The first cities appeared in Mesopotamia around 5,000 years ago. The Roman Empire, from its traditional founding to its fall in the West, spanned about 1,200 years. All of recorded human history, from the first Sumerian clay tablets to this moment, covers less than 6,000 years. Voyager 1 will spend somewhere between 2 and 5 times the entire span of recorded human civilization simply crossing the outer reaches of its home solar system. It could have gone faster. It could have been aimed differently. It could have been launched a year earlier or a year later and found an entirely different trajectory. But it was aimed as it was, launched when it was, and sent in the direction it was, and so the path is fixed. Now we turn to what waits on the other side. In approximately 40,000 years, something remarkable will happen. 2 remarkable things, in fact, one for each spacecraft. Voyager 1, heading in the general direction of the solar apex, the direction in which the Sun itself is moving relative to nearby stars, will pass within 1.6 light-years of a star called Gliese 445, currently located in the constellation Camelopardalis, the Giraffe. In the year 40,272 AD, more than 38,200 years from now, Voyager 1 will come within about 1.7 light-years of an obscure star in the constellation Ursa Minor as well. These are not close approaches in any human sense. At 1.6 light-years, Gliese 445 will be roughly 38% of the distance that currently separates us from the Alpha Centauri system. Voyager 1 will not enter any star's planetary system. It will not be captured. It will pass through the neighborhood of that star the way a leaf drifts past a distant lighthouse, never illuminated, never drawn in. Pause here, because this image deserves attention. 40,000 years from now, a machine built by human hands will drift through the outer neighborhood of a distant star. No one will be watching. No instrument on Voyager will register the encounter, because every instrument will have been dark for thousands of years. The spacecraft itself will feel nothing, of course, because spacecraft feel nothing. But the geometry will be precise. It will happen. It is in mathematics, as fixed and certain as the mathematics that puts the sun in its place in the sky each morning. Voyager 2 has its own close approach at approximately the same time frame. The spacecraft will swing within about 1.7 light-years of Ross 248, a small red dwarf star in the constellation Andromeda, in approximately 40,000 years. Ross 248 is a dim red dwarf star with roughly 12% of the Sun's mass. Corinne Baylor-Jones at the Max Planck Institute for Astronomy in Germany and Davide Farnocchia at the Jet Propulsion Laboratory have performed detailed calculations using the 3-dimensional map of star positions and velocities throughout the Milky Way, provided by the European Space Agency's Gaia spacecraft since 2014. Their calculations used a database of more than 1 billion precisely mapped stars to work out which stars the spacecraft will rendezvous with in the coming millennia. The closest encounters for all spacecraft take place at separations between 0.2 and 0.5 parsecs within the next 1,000,000 years. These are not collision courses. They are gravitational whispers. At these distances, neither star's gravity will meaningfully alter the path of either Voyager. The spacecraft will continue on, bent by the encounter by perhaps a tiny fraction of a degree, and pass out the other side of the stellar neighborhood, still moving at effectively the same speed in effectively the same direction. In roughly 296,000 years, Voyager 2 will swing within about 4.3 light-years of Sirius, the brightest star in Earth's sky. Sirius is a blue-white star, roughly twice the mass of the Sun, and it burns with nearly 25 times the solar luminosity. From 4 light-years away, it would appear to any observer traveling with Voyager 2 as an extremely bright star in an otherwise black sky. It would not look close. It would look the way distant lights look from a ship at sea, present but unreachable. Roughly 100,000 years after that close approach to Sirius, Voyager 2 will be brushed by 2 more stars, known as Delta Pavonis and GJ 754. The pattern here is becoming clear, and it carries a strange kind of beauty. The Voyagers are not heading toward anything. They were never aimed at a destination. They were aimed outward, generally away from the planetary system that spawned them, and the galaxy has placed these particular stars in their general path by the same cosmic coincidence that places any 2 objects near each other in the vast structure of the Milky Way. The encounters are accidental. Every single one of them is accidental. And yet they will happen, precisely as the mathematics predicts, tens of thousands of years after every human being alive today has turned to dust. This is worth settling into. The fact that we can calculate these encounters at all is itself a kind of wonder. That we know where Gliese 445 is, know its velocity, know its distance, know the precise trajectory of a spacecraft built in the 1970s, well enough to predict their nearest approach to better than a light-year's precision across 40,000 years of future time, is an extraordinary testimony to the reliability of the laws of physics. The laws that govern gravity do not change. They have not changed since the first moments of the universe. They will not change in 40,000 years. The calculation works because the universe is consistent. Roughly 500,000 years have passed in our journey. Take stock of where we are. Voyager 1 is somewhere in the interstellar medium north of the galactic plane, having drifted past several stellar neighborhoods, none of which captured it. It continues at 17 kilometers per second, more or less. Voyager 2 is somewhere below the galactic plane, having swept past Ross 248 and eventually Sirius and those 2 subsequent stars, none of which captured it either. Both spacecraft have been utterly silent for nearly 500,000 years. No signals, no instruments, no power. Just mass and velocity and the geometry of Newton's laws playing out with absolute fidelity. The golden records are still attached to each spacecraft. In the cold, hard vacuum of interstellar space, there is no weather, no rain, no oxidation, no bacterial decay. The greatest enemy of the record's surfaces is the slow, patient bombardment of interstellar dust and cosmic rays. Researcher Charles Oberg and his colleagues, inspired by the 2018 release of the second batch of data from the European Space Agency's Gaia spacecraft, combined tracking the Voyager's trajectories forward with studying the environments the spacecraft will fly through to estimate the odds of the golden record surviving their adventures while remaining legible. The result was a forecast that stretches beyond humanity's likely extinction, beyond the collision of the Milky Way with the neighboring Andromeda galaxy, and beyond even the extinction of most stars. Both golden records have good odds of remaining legible, since their engraved sides are tucked away against the spacecraft bodies, shielded from the worst of the interstellar bombardment. The outer surface of Voyager 1's record is more likely to erode away. But the information on Voyager 2's record is more likely to become illegible, because the orbit that Voyager 2 is flung into over billion-year timescales is more chaotic and significantly more difficult to predict with certainty, meaning it will fly through environments harder to model. Both golden records are highly likely to survive at least partially intact for a span of over 5 billion years. 5 billion years. The age of the Earth, the remaining lifespan of the Sun, both held in a single number describing the endurance of a 12-inch copper disc. Now we move into timescales where the word million starts to feel too small. Something else needs to be established before the journey goes further. Something about the nature of the Voyager's motion through the galaxy. Neither spacecraft has galactic escape velocity. This is a crucial physical fact. To leave the Milky Way entirely, an object would need to be moving fast enough to overcome the combined gravitational pull of hundreds of billions of stars, the dark matter halo surrounding the galaxy, and the distributed mass of all the gas and dust in between. Voyager 1 is moving at about 17 kilometers per second relative to the Sun. The galactic escape velocity from our position in the Milky Way is something on the order of 550 kilometers per second. Voyager 1 is not even close. It will never leave the Milky Way under its own momentum. Neither will Voyager 2. Instead, both spacecraft will do something that seems simple, but is, on reflection, extraordinary. They will enter into independent orbits around the center of the Milky Way. Right now, the Sun orbits the center of the Milky Way galaxy. It is not stationary. It is moving at roughly 220 kilometers per second around the galactic core, completing one full orbit approximately every 225 to 250 million years. When the Voyager spacecraft departed the solar system, they borrowed some of this orbital motion, the way a ball thrown from a moving train carries the train's momentum. The Voyagers are not stationary relative to the galaxy. They are orbiting. They will orbit on their own, completing a loop through the Milky Way every 225 million years for billions of years, until a collision with another galaxy disrupts this orderly flow, in the words of Voyager project scientist Edward Stone, who spent decades overseeing the mission's science operations. 225 million years per galactic orbit. In one orbit, the landscape of life on Earth transforms completely. When the solar system was last at this position in the Milky Way, the Triassic period had barely begun, and the first dinosaurs were still tens of millions of years in the future. In one orbit of the galaxy, dinosaurs rose, ruled for 165 million years, and vanished. The mammals diversified. Primates appeared. Humans evolved, built cities, launched spacecraft. And the solar system returned to roughly where it had been when those first hesitant reptiles walked the supercontinent of Pangaea. Now multiply that span by 20 or 30, and you begin to approach the timescales at which the Voyagers will be orbiting when the next major event in their story unfolds. In roughly 4 to 5 billion years from now, the first close approach of the Milky Way and the Andromeda Galaxy will occur, according to models published in Astronomy and Astrophysics in 2020. Some earlier estimates, including work by Cox and Loeb in 2008, placed the first approach at about 2.8 billion years from now, and the full merger at about 5.4 billion years. More recent data from the Gaia satellite which has measured the velocities of Andromeda's stars with unprecedented precision, suggests the process will unfold over approximately 10 billion years in total from now. The uncertainty comes from the difficulty of precisely measuring Andromeda's transverse velocity, the component of its motion perpendicular to our line of sight. This is one of the genuine limits of our current knowledge, and it is worth naming plainly. We do not know exactly when the merger will occur, or exactly how the resulting gravitational chaos will ripple through the merged system. What we do know is this: galaxy mergers are not collisions in any ordinary sense. The distances between individual stars are so vast that when two galaxies merge, the probability of any individual star colliding with another is vanishingly small. The stars pass through each other like two swarms of bees merging in midair, each bee surrounded by miles of open space. The galaxy is almost entirely emptiness, and the merger is almost entirely the gravitational reshuffling of that emptiness. But for the Voyagers, the merger matters in a different way. Astrophysicist Charles Oberg noted in his research that the gas clouds within the merging galaxies have so much mass concentrated in one place that they may actually bend the trajectory of the spacecraft and fling them into new orbits, sometimes much farther out, sometimes even deeper toward the galactic core. This is the point at which predictions begin to branch. Voyager 1's trajectory, already aimed above the galactic plane, may send it oscillating wildly through the merger's gravitational chaos. Voyager 2's path is harder to model still, because its orbit is more chaotic from the outset. Both probes may be ejected into dramatically larger galactic orbits. Both may be scattered toward the dense core of the newly merged galaxy, which astronomers call Milkomeda. Both may end up drifting through regions of much higher stellar density than they currently traverse. Throughout this galactic orbit in the current era, the Voyager spacecraft oscillate up and down, with Voyager 1 doing so more dramatically than its twin. According to models, Voyager 1 will travel so far above the main disk of the galaxy that it will see stars at just half the density as we observe from Earth. It will spend significant time in the halo of the galaxy, that sparse outer region of old stars and dark matter that surrounds the bright disk, the way an atmosphere surrounds a planet. By 500 million years from now, the solar system and the Voyagers alike will complete a full orbit through the Milky Way. There is no way to predict what will have happened on Earth's surface by then. But it is a time span on the scale of the formation and destruction of Pangaea and other supercontinents. Within a billion years, research by astronomer Avi Loeb of Harvard University and his student Shokruz Kakarov, who in 2024 calculated the galactic orbits of all 5 NASA probes launched on interstellar trajectories, using a detailed model for the mass distribution of the Milky Way galaxy, indicates that Voyager will reach the opposite side of the Milky Way disk relative to the Sun. By the time it gets there, the Sun will have changed beyond recognition. Stellar evolution models predict that within about a billion years, the Sun will have grown luminous enough to drive Earth's oceans into a runaway evaporation. The oceans which have covered this planet for 4 billion years, which nurtured the first life, which shaped every coast, every storm, every current of weather, in every age of human history, will simply boil away. NASA, as Loeb dryly observes, might not be around to celebrate this remarkable milestone in Voyager's journey. This particular observation, simple as it is, carries a weight that lands slowly. The mission that launched these two spacecraft will have been forgotten longer than human civilization has existed before the spacecraft reaches the opposite side of the galaxy. The civilization that built them, the languages in which the records were greeted, the cultures whose music fills the grooves of the golden record, all of it gone before the spacecraft finishes its first full crossing of the galactic disk. It will keep going. It will keep going after the oceans evaporate. It will keep going after the sun expands into a red giant, swallowing Mercury, then Venus, perhaps reaching the orbit of Earth itself. It will keep going after the sun collapses into a white dwarf, a dense, cooling cinder of carbon and oxygen, roughly the size of Earth, but carrying half the sun's current mass. It will keep going. On a geological timescale 300 kilometers above any hypothetical observer on a hypothetical planet, the two aluminum spacecraft drift outward in silence. They carry no fuel. They carry no heat. They carry no light. They carry only mass and velocity and a thin gold-plated disk on which a species once placed its most earnest attempt to say, "We were here. We knew beauty. We made music." The scale of what lies ahead is such that the Oort Cloud, the galactic orbit, the merger with Andromeda, all of it, all those billions of years of travel, are merely the opening chapters of the story. The real vastness begins when the stars go out. Roughly 5 billion years from now, pause here and look back at what has passed. The sun is gone. Or rather, it is no longer the sun. It has swelled into a red giant, enormous and dim, its outer layers having expanded to perhaps 100 times their current radius. Whether Earth survives inside that expanding envelope is a matter of genuine scientific debate. Some researchers, including Klaus-Peter Schroeder and Robert Conan Smith, in their 2008 paper published in the monthly notices of the Royal Astronomical Society, calculated that the Sun's expanding surface will actually engulf Earth's orbit before the red giant phase ends. Others argue that as the Sun loses mass during the giant phase, Earth's orbit will drift outward fast enough to stay ahead of the expanding surface. We do not know with certainty which is correct. What we do know is that by the time the Sun reaches its red giant maximum, any surface liquid water on Earth will have been gone for roughly 1 billion years, and any surviving remnant of life will be unrecognizable by any standard we currently hold. The Sun then sheds its outer layers in a slow, beautiful exhalation called a planetary nebula. A shell of ionized gas spreads outward from the stellar core, glowing in reds and greens and blues, illuminating the inner solar system one last time with a light that has nothing to do with fusion, nothing to do with the hydrogen burning that powered everything for 10 billion years. What remains at the center is a white dwarf, roughly the size of Earth, roughly half the current mass of the Sun, composed of carbon and oxygen, slowly radiating the heat of its collapse into space. The planetary nebula fades. The white dwarf glows, then dims, then continues dimming over billions of years. In the cold dark of whatever remains of the solar neighborhood, the former Sun becomes a cooling ember. And through all of this, the Voyagers have been traveling. The Oort Cloud they traversed in those first tens of thousands of years is now gone, dissipated over hundreds of millions of years by the gravitational tugs of passing stars. The region of space the Voyagers occupy has changed in composition, in stellar density, in the precise flavor of interstellar magnetic fields threading through it. But the Voyagers themselves are largely unchanged. Metal does not rust in a vacuum. Circuits do not corrode when there is nothing to corrode them. The long, slow bombardment of interstellar dust has pitted their surfaces and eroded their most exposed components over the billions of years. But the bodies of the spacecraft, built from aluminum and titanium and various alloys, remain substantially intact. The golden records, their engraved faces pressed against the spacecraft bodies, have survived. Something here deserves attention. The information encoded on those records, 116 images, spoken greetings in 55 languages, music drawn from cultures that no longer exist in any recognizable form, the sound of rain on leaves, the sound of a mother's first words to her child is still there, etched into the surface of copper, preserved under gold, protected by the geometry of its own mounting. The spacecraft will never play it again. There is no power left to run a playback system, even if one existed. But the grooves are there. The information persists. By 5 billion years from now, the Milky Way and Andromeda galaxy are in the first stages of their collision. The process began earlier, when their gravity first began to distort each other's shapes, when tidal forces pulled long streams of stars out from each galaxy's disk in great arcing bridges of light called tidal tails. The merger unfolds over billions of years, not in an instant. There is no explosion, no single catastrophic moment. Instead, there is a slow gravitational dance, the two galaxies swinging past each other, separating slightly, then drawn back together by their mutual gravity, swinging past again, each pass causing more disruption, more scrambling of stellar orbits, more chaos in the previously orderly rotation of each galaxy's disk. Throughout this period, some researchers think the Voyagers may be scattered into dramatically different orbits by the gravitational chaos of the merger. Others think the spacecraft, being so small and so far from the densest regions of either galaxy, will mostly follow the general reshuffling of stellar orbits without any single dramatic encounter. Some researchers believe the merger's most violent gravitational effects will be concentrated near the two galactic cores, where the two supermassive black holes at the centers of the Milky Way and Andromeda will eventually spiral together. The Voyagers, orbiting at what would be considered suburban galactic distances, may experience the merger as a slow, multi-billion-year reshuffling of the scenery, rather than as a sudden catastrophe. The merged galaxy, now called Milkomeda by some cosmologists, is a different shape from either predecessor. The neat spiral arms are gone, scrambled into a more diffuse elliptical structure. The sky, if there were any eyes to see it, would look nothing like the sky visible from Earth tonight. Different stars in different positions, different structures overhead. The familiar constellations, of course, are long gone. They were already unrecognizable within a few tens of thousands of years, as the stars that compose them drifted apart on their own independent galactic orbits. This is a good moment to restate something planted at the very beginning of this story, and to feel it with the full weight of everything we have covered since. These two spacecraft are not heading toward any destination. They were never aimed at anything. The people who built them were thinking about 10 years of science, about close-up photographs of Jupiter's moons, about the magnetic fields around Saturn, about a once-in-175 years alignment of planets that Gary Flandreau had noticed in 1964. Nobody in that chain of decision-making was thinking about the merger of the Milky Way with Andromeda. Nobody was thinking about white dwarfs. Nobody was thinking about 10 trillion years. And yet the spacecraft are heading there all the same, carried forward by laws that nobody chose and that nobody can revoke. Several billion more years pass. Take stock of where we are. Milkomeda is settling into a more stable configuration. The two supermassive black holes at its center have merged or are in the process of merging, releasing gravitational waves that wash through the surrounding space like ripples from a stone dropped into still water. These gravitational waves carry enormous energy, but have no meaningful effect on objects as small and as distant as the Voyagers. The Voyagers drift on. Around them, the stellar population of Milkomeda is aging. The galaxy formed most of its stars in bursts of activity billions of years ago, and those stars have been evolving ever since. The most massive stars, which burn hottest and fastest, are long gone, having exhausted their fuel in millions rather than billions of years, and collapsed into neutron stars and black holes early in the galaxy's history. The medium-mass stars, stars like the Sun, have been going out over the billions of years since the merger, each one swelling into a red giant, shedding its outer layers, leaving a white dwarf behind. What remains in abundance are the smallest, most frugal stars. The red dwarfs, sometimes called M-class stars, which burn so slowly and so dimly that they can sustain fusion for tens of billions, or even hundreds of billions, of years. Red dwarfs are not glamorous. They are dim and cool, glowing in deep orange and red, many of them too faint to see with the naked eye, even from relatively close distances. But they are extraordinarily numerous. In the Milky Way today, roughly 3 out of every 4 stars are red dwarfs, and their lifespans make the Sun look profligate. A red dwarf with half the Sun's mass may burn for 50 to 100 billion years. A red dwarf with a quarter of the Sun's mass might sustain fusion for 1 trillion years. The universe is currently only about 13.8 billion years old. Not a single red dwarf star in the history of the universe has yet died of old age. Every red dwarf that has ever formed is still burning. So as we move into timescales measured in hundreds of billions of years, the galaxy around the Voyagers is not pitch dark. It is sparsely lit, dimly glowing, dominated by these small red stars that burn with a patience that makes the Sun look hasty. Around 100 trillion years from now, the last of the red dwarf stars will exhaust their fuel. 100 trillion years. The number is so large that even the comparison to human timescales begins to lose meaning. The age of the universe is 13.8 billion years. 100 trillion years is roughly 7,000 times longer than the current age of the universe. It is a number that makes our entire cosmic history look like the first few minutes of a very long story. This era, from roughly 10 billion to 100 trillion years from now, is what cosmologists Fred Adams of the University of Michigan and Gregory Laughlin of Yale University, in their 1997 paper, A Dying Universe, The Long-Term Fate and Evolution of Astrophysical Objects, called the Stelliferous Era, the Age of Stars. We are living in it right now. Every star you can see tonight is part of it. Every star that has ever shone in any sky, anywhere in the universe, is part of it. And it will end. Adams and Laughlin mapped the far future of the universe using a framework of cosmological decades, where each decade represents a factor of 10 increase in time. We currently live at roughly cosmological decade 10, meaning the universe is on the order of 10 to the 10th power years old. The era of new star formation effectively tapers off by around cosmological decade 13 to 14, meaning somewhere between 10 and 100 trillion years from now, as the raw material for star formation is largely consumed or scattered. After new star formation ends, the existing stars burn through their remaining fuel over the following tens of trillions of years. The last red dwarf goes dark at around cosmological decade 14 to 15, 100 trillion years. When that last red dwarf exhales its outer layers and collapses into a white dwarf, the Stelliferous Era ends. The galaxy, Milkomeda, becomes a dim place. It is not quite dark because white dwarfs glow, gradually cooling from the residual heat of their formation. But there is no more fusion, no more hydrogen converting to helium in stellar cores, no more starlight in the sense we understand the word. The universe enters what Adams and Laughlin called the degenerate era. Here is where the Voyager's story becomes something genuinely difficult to hold in the mind. Through all of this, they have been traveling. They have been traveling since September 1977. They have crossed the outer Oort Cloud. They have passed through the gravitational neighborhoods of several stars without being captured by any of them. They have been carried along by the orbital motion of the solar system, then freed into their own independent galactic orbits. They have experienced, in some loose gravitational sense, the merger of two galaxies. They have watched, though watched is entirely the wrong word, because there are no instruments left to watch with. The stars go out one by one over hundreds of billions of years, and they are still moving at roughly the same speed, the same 17 kilometers per second, give or take whatever gravitational encounters have nudged them over the eons. This is the aspect of the Voyager story that is hardest to internalize. There is no decay in their motion. There is no running out of momentum. An object in motion in the vacuum of space does not slow down. It does not get tired. It does not require fuel. The energy of their motion was invested in them by the rockets and the gravity assists of 1977, and nothing in the interstellar void has taken that energy from them. Every kilometer per second of velocity they had when they left the solar system, they still have now, modified only slightly by the gravitational encounters along the way. 100 trillion years from now, when the last star goes dark, both Voyagers are still moving. Something here wants to be felt as well as understood. Picture the galaxy at this moment, not as a spiral of light as you see it in photographs, but as what it actually is by this point. A vast, dark, slowly dispersing cloud of stellar remnants. White dwarfs, glowing faintly in their slow cooling. Neutron stars, spinning in the dark with no pulsar beam left to announce themselves. Black holes, formed from the most massive stars, drifting in the galactic halo with no surrounding material left to illuminate them. And threaded through all of this dark, cooling material, the occasional surviving relic of the Stelliferous Era, objects too small to ignite fusion in the first place, brown dwarfs and rogue planets, and, impossibly, two small aluminum spacecraft traveling at 17 and 15 kilometers per second respectively, carrying gold-plated records and decades of human yearning pressed into copper. The galaxy itself is changing in another, slower way. Over hundreds of billions to trillions of years, the stellar remnants in a galaxy do not simply sit still. They interact. They pass close to each other over the eons, exchanging tiny gravitational nudges. Some of these nudges, accumulated over unimaginable spans of time, are enough to eject objects from the galaxy entirely, flinging them into the void between galaxies with a gentle gravitational kick delivered over millions of years of near encounters. Others are enough to send objects spiraling slowly inward toward the central black hole. Fred Adams and Gregory Laughlin estimated in their 1997 work that virtually all surviving degenerate remnants are eventually isolated on sufficiently long timescales, approximately 10 to the 20th power years, as galaxies evaporate through gravitational scattering. 10 to the 20th power years. That is 100 million trillion years, a number that makes 100 trillion look like a rounding error, and it is merely an intermediate waypoint in the journey we are following. By 10 to the 20th years, through the slow gravitational scattering of trillions of near encounters over unimaginable time, most of the stellar remnants in what was once Milkomeda will either have been ejected into the intergalactic void or accreted onto the central supermassive black hole. The galaxy itself, in the sense of a coherent structure with recognizable geometry, will be largely dissolved. Some researchers believe the Voyagers, being very small and very far from the most densely interacting regions of the galaxy, might survive this dissolution phase without being dramatically perturbed. Their orbits might slowly, over trillions of years of accumulated tiny gravitational nudges, drift in ways that are entirely impossible to calculate. The mathematics of gravitational scattering at these timescales is inherently chaotic, meaning that tiny uncertainties in initial conditions propagate into enormous uncertainties in final positions. We genuinely cannot know where either Voyager will be at 10 to the 20th years. This is one of the hard limits of physics, an epistemological wall, not just a wall of current ignorance, but a wall built into the nature of chaotic dynamical systems. We cannot know, not approximately, not within a large range of uncertainty. We cannot know. What we can say is this: at whatever point the remains of Milkomeda have dispersed, the Voyagers are somewhere in the universe, still moving, still carrying their records, still composed of atoms that have not yet found any reason to rearrange themselves. Now we turn to a question that sits at the heart of everything. How long do those atoms last? There is a particle at the center of every atomic nucleus. It is called the proton. Along with the neutron, it is what makes ordinary matter ordinary. The chair you sit in, the air you breathe, the spacecraft we have been following across cosmic history, all composed of atoms whose nuclei are built from protons and neutrons. And here is the question that particle physics has been wrestling with for decades. Does the proton last forever? In most versions of the standard model of particle physics, the proton is considered stable. It does not decay. It persists indefinitely. But in extensions of the standard model, particularly in grand unified theories that attempt to merge the strong and electro-weak forces into a single framework, protons do decay. They transform over enormously long timescales into lighter particles, releasing a small amount of energy in the process. The predicted proton lifetime in many of these theories is around 10 to the 34th power years, or longer. In some theories, it is stable indefinitely. The experimental evidence is frustratingly ambiguous. Experiments conducted deep underground, in mines and under mountains, in detectors like Super Kamiokande in the Mozumi mine beneath Mount Ikino in Japan, have searched for proton decay for decades. As of the current state of knowledge, no proton has been definitively observed to decay. This has ruled out some of the simpler grand unified theories. those that predicted Proton lifetimes shorter than about 10 to the 34th years. But it has not ruled out all of them. We do not know with certainty whether protons are stable or not. This uncertainty matters profoundly for the Voyagers. If protons are stable, the spacecraft persist indefinitely. The aluminum and titanium and copper of their construction simply sit there, cooling to whatever temperature the universe achieves in its distant future, but remaining structurally intact for timescales that dwarf everything else in this story. If protons eventually decay, the spacecraft dissolves. Not violently, not suddenly, but particle by particle over timescales of 10 to 34th years or longer, each proton eventually converting into lighter particles, each atom gradually losing its nuclear stability, each piece of aluminum slowly becoming something else, until nothing of the original spacecraft structure remains. 10 trillion years sits well below either threshold. 10 trillion years is 10 to the 13th power years. Proton decay, if it occurs at all, happens at around 10 to 34th years. Stellar remnants, like white dwarfs, cool, but do not dissolve on timescales of 10 trillion years. The galaxy has not yet evaporated on that timescale. Everything we have described, the red dwarfs still burning, the stellar remnants drifting in Milkomeda, the slow gravitational scattering of the galactic remnants, all of this is ongoing at 10 trillion years. So where are the Voyagers at 10 trillion years specifically? 10 trillion years is roughly 725 times the current age of the universe. The last star formation in Milkomeda or any other galaxy will have ended somewhere around 1 trillion years from now, 10 times the current age of the universe. So by 10 trillion years, we are 9 trillion years past the end of new star formation. Every hydrogen-burning star that was going to form has already formed and died. Every red dwarf that was going to shine has already exhausted its fuel and become a white dwarf. The universe, at 10 trillion years, is in the early stages of the degenerate era, a cosmos populated by cooling white dwarfs, neutron stars, black holes, and the vast expanses of almost nothing between them. This is what the universe looks like in 10 trillion years. The two Voyager spacecraft, having been in motion for 10 trillion years since their launch, will have covered an almost incomprehensible distance. Consider the arithmetic, stated plainly. Voyager 1 travels at approximately 17 kilometers per second. There are roughly 31.5 million seconds in a year, so Voyager 1 covers about 536 million kilometers per year, which is a little over 3.5 astronomical units per year. Over 10 trillion years, at a speed of 3.5 astronomical units per year, Voyager 1 would have covered approximately 35 trillion astronomical units if its motion were perfectly uniform. A light year is about 63,241 astronomical units. So 35 trillion astronomical units corresponds to roughly 553 million light years. 553 million light years. This number is almost certainly an overestimate of the actual straight-line distance from wherever the Voyagers began that journey, because gravitational encounters along the way will have curved and redirected their paths many times. But it gives a sense of the scale. 500 million light years of cumulative travel, measured along whatever winding path gravitational encounters have imposed on the spacecraft over 10 trillion years. For comparison, the distance to the Virgo cluster of galaxies, the nearest large cluster of galaxies to the Milky Way, is about 65 million light years. The Voyagers will have traveled the equivalent of crossing and recrossing a structure that large many times over, within the gravitational confines of whatever remains of the Milky Way Andromeda merger. But here is where the question of where becomes genuinely difficult to answer, and why the answer is deeply, honestly uncertain. The Voyager's actual location at 10 trillion years depends on the accumulated history of every gravitational encounter they experience along the way. This is a chaotic system in the technical sense of that word. Tiny variations in initial conditions, in the precise trajectory of every star they pass near, in the exact timing of the galactic merger's scrambling of orbits, compound over time into massive differences in final position. Some models suggest the spacecraft may by this point have been gravitationally scattered into the halo of what remains of Milkomeda, orbiting at great distances from the galactic center in the sparse outer regions. Some models suggest one or both may have been ejected into the intergalactic void entirely, traveling through the darkness between the merged Milkomeda structure and other galaxy clusters. The researchers who have studied this, including Avi Loeb and his student Shokruz Kakarov at Harvard, and Corinne Baylor-Jones at the Max Planck Institute, acknowledge that beyond a certain horizon of time, the specific location becomes fundamentally unpredictable. The chaotic nature of gravitational scattering means the question of precisely where Voyager 1 or Voyager 2 will be in 10 trillion years does not have a calculable answer. Not one we can calculate now. Not one that will become calculable with better instruments. It is an inherent feature of chaotic dynamics applied to astronomical timescales. What we can say is that the Voyagers will be somewhere in or near the remnants of Milkomeda, possibly in the halo, possibly in the intergalactic medium, still moving, still carrying their records. The Voyagers will be drifting through what would be, to us, a completely unrecognizable galaxy, free of so-called main sequence stars, populated almost exclusively by black holes and stellar remnants such as white dwarfs and neutron stars, in the words of researcher Charles Oberg. The only source of significant illumination in this epoch will be supernovas that result from the once-in-a-trillion-year collision between these stellar remnants that still populate the galaxy. Once in a trillion years. A flash of light in an otherwise dark cosmos. Two small spacecraft drifting through the dark, having traveled since the era of living stars, still moving, still intact, waiting in silence for the next impossible flash. Something needs to be established at this point in the journey. Something about the texture of the universe at 10 trillion years that no distance calculation quite captures. The darkness is not empty. When we say the Stelliferous Era has ended, when we say the last stars have gone out, we are describing the end of visible light as a dominant feature of the cosmos. We are not describing the end of matter. We are not describing the end of the structure. The universe at 10 trillion years is full of things. They are cold, dark, and widely separated, but they are there. White dwarfs, the cooling remnants of stars like the Sun, each one roughly Earth-sized, composed of crystallized carbon and oxygen, radiating the last of their formation heat into space. Neutron stars, city-sized objects of extraordinary density, the collapsed remnants of massive stars spinning in the dark with no surrounding material left to illuminate them, carrying magnetic fields of crushing intensity around objects so dense that a teaspoon of their material would weigh 1 billion metric tons. Black holes, both the stellar mass variety formed from the most massive individual stars and the supermassive variety that sit at the centers of galaxies. including the one that formed from the eventual merger of the Milky Way's Sagittarius A star with the Andromeda's far more massive central black hole. And scattered among all of this, moving through it at speeds that are slow on galactic scales, but extraordinary on human ones, 2 aluminum spacecraft. Consider what the environment feels like around the Voyagers at this point in the journey, not in numbers, but in sensation. The cosmic microwave background radiation, the afterglow of the Big Bang, has been cooling since the universe was 380,000 years old. Right now, it corresponds to a temperature of about 2.7 Kelvin, just 2.7 degrees above absolute zero. By 10 trillion years from now, the universe has expanded so dramatically that this background radiation has cooled to a temperature that is a tiny fraction of even that already vanishing warmth. The universe is colder than any laboratory on Earth has ever achieved. It is colder than the interior of any object ever constructed by any civilization. It approaches, but does not reach absolute zero, because the dark energy driving the universe's expansion does not permit a true thermal equilibrium. The universe is not quite at heat death, but it is approaching something that looks very much like it from a distance. The spacecraft themselves, having radiated away their residual warmth over billions of years, have equilibrated to whatever temperature the surrounding universe maintains. They are cold, not cold in the way a window pane is cold on a winter morning. Cold in the way that makes any ordinary human intuition about temperature meaningless. The electrons in the atoms of Voyager's aluminum frame still move, because they always move, but barely. The atoms themselves vibrate with the vanishing minimum of thermal energy their environment provides. The spacecraft are as close to motionless in their atomic vibration as matter can get without ceasing to be matter. And yet, they move. At 17 kilometers per second, Voyager 1 still moves. This is the moment to ask the questions that the journey so far has been preparing us for. Not to answer them, because some of them cannot be answered, but to ask them in the right order, with the full weight of what we now know pressing on each one. What does it mean for humanity that these objects will outlast every living thing? What does it mean that we built machines in a moment of scientific ambition and political compromise that will persist through the death of stars? What does it mean that the most durable thing our civilization ever produced is not a library, not a monument, not a city, but 2 spacecraft aimed at nothing in particular, carrying a record of everything we considered worth preserving? What will the universe do with them over the timescales that follow 10 trillion years? And what does the question of what the universe will do with them tell us about what the universe is? These questions do not resolve cleanly. They pile on each other, each one heavier than the last. Is there any civilization anywhere in the observable universe that might find one of these spacecraft before the last stars go dark? We cannot know this. We do not know whether intelligent life exists anywhere beyond Earth. We do not know whether, if it exists, it is capable of interstellar travel. We do not know whether, if it is capable of interstellar travel, it would recognize the Voyagers as artifacts of intelligence rather than as debris. Carl Sagan, who chaired the committee that designed the Golden Record, believed the probability was meaningful. He believed that the universe contained enough time and enough stars for the emergence of technological civilizations to be something other than miraculous, and that a civilization capable of finding the Voyagers would almost certainly be capable of reading the record. Other researchers are more skeptical. Some think the probability of any encounter between the Voyagers and an alien civilization approaches zero, not because intelligent life is necessarily absent, but because the galaxy is so large, the Voyagers are so small, and the timescales of drift so vast that the probability of intersection is, in practical terms, indistinguishable from zero. We cannot know which view is correct. We genuinely cannot. This is not a statement about temporary ignorance, about something we will eventually measure our way to clarity on. It is a statement about the fundamental limits of what is knowable from where we stand. What, then, would an alien civilization encounter if one were somehow to find Voyager on drifting through the degenerate era in the dim light of cooling white dwarfs? A spacecraft that looks nothing like any technological artifact they have ever encountered, because their civilization emerged billions of years after ours ended. A machine built from aluminum and titanium, materials that any sufficiently advanced civilization would recognize as processed, refined, structural. Bolts and brackets that speak of a technology that worked with mechanical fasteners, suggesting a civilization that had not yet mastered molecular assembly or programmable matter. A large dish antenna, still oriented roughly toward where the sun once was in the galaxy, long since moved to a different galactic address by the merger and the gravitational scattering of billions of years. And on the side of the spacecraft, a disk, a 12-inch copper disk plated in gold with a cover etched in diagrams. Diagrams showing the hyperfine transition of hydrogen, the most abundant element in the universe. Diagrams showing the position of the solar system relative to 14 pulsars, the radio-emitting neutron stars whose precise spin rates served as a navigational reference in 1977. Most of those pulsars will have slowed and gone silent by the degenerate era. But the pattern of their positions, like a stellar fingerprint, might still be recognizable to a civilization with sufficiently detailed maps of where stars once were. The uranium-238 electroplated into the cover will have partially decayed. Its half-life is 4.5 billion years, the same as the age of the Earth. By 10 trillion years, it will have gone through approximately 2,200 half-lives. The uranium-238 will be almost entirely gone, converted through its decay chain into lead-206. A civilization that measures the ratio of remaining uranium to accumulated lead will know something extraordinary. They will know how long the record has been traveling. They will know that someone built this object at a specific moment in cosmic time and sent it outward into space. They will know that whoever built it understood physics well enough to use radioactive decay as a clock. They will know that whoever built it expected the record to be found. Whether they can read it is a different question. The record requires a technology analogous to a phonograph needle, a mechanical stylus tracing physical grooves, converting physical displacement into vibration. Whether any civilization in the degenerate era would possess or reconstruct such a technology is genuinely unknowable. But the attempt was made. That is what the golden record is. An attempt made in full awareness that it might fail, made anyway, because the alternative was silence. Stay with this for a moment. The people who built the Voyagers were not naive about the odds. Carl Sagan was not naive. He understood that the probability of the golden record ever being found and read was small. He understood that the universe is vast, that the spacecraft are tiny, that the timescales involved made the concept of finding the record almost philosophical rather than practical. He built it anyway. He committed to the attempt. He chaired the committee. He argued for the whale songs and the bark and the greeting in Sumerian. He chose to behave as though the universe contained something worth communicating with. That choice, made in 1977 by a scientist at Cornell University who would not live to see Voyager 2 reach Neptune, is now encoded into the physical structure of an object that will outlast every civilization on Earth, every star in the galaxy, and possibly the galaxy itself in its current form. This is worth pausing on, not because it resolves anything, but because it illuminates the character of the human endeavor at its best. There is something in us that reaches outward, something that refuses the comfortable silence, something that builds the record even when the mathematics says it will almost certainly never be found. Roughly 10 trillion years from now, as we have established, the universe is deep into the degenerate era. This is the moment to examine what happens next, not in the next few billion years, but in the unimaginably long march that follows. Because beyond 10 trillion years, several processes begin that will transform even the remnants of what the Stelliferous Era left behind. The first is the continued cooling of white dwarfs. White dwarfs are not burning. They have no ongoing fusion. They shine entirely on the borrowed heat of their formation, the gravitational energy released when their parent stars collapse. Fred Adams of the University of Michigan and Gregory Laughlin of Yale noted in their landmark 1997 survey of the universe's far future that white dwarfs will cool to equilibrium with the cosmic background radiation at sub-Kelvin temperatures in the far future, eventually crystallizing completely, becoming what some astrophysicists call black dwarfs. A black dwarf is a white dwarf that has cooled to the point of emitting no detectable radiation. It is, in effect, a cold, dark, crystalline sphere of carbon and oxygen the size of Earth, drifting through the darkness, invisible to any instrument that relies on electromagnetic radiation. The timescale for this cooling is relevant. White dwarfs cool slowly. A white dwarf with the mass of the Sun takes on the order of a few quadrillion years to cool to near background temperatures. A quadrillion is 10 to the 15th power years. This is longer than 10 trillion years by a factor of 1,000. So at 10 trillion years, white dwarfs are still visible, still warm, still faintly glowing in the infrared. The degenerate era at 10 trillion years is early. The dimmest, coldest phase is still far ahead. The second process is neutron star cooling, which follows a similar but faster trajectory. Neutron stars, formed from the collapse of massive stars, cool on timescales of millions to billions of years. By 10 trillion years, most neutron stars formed in the Stelliferous Era have cooled to temperatures indistinguishable from the cosmic background. They drift in the dark, detectable only by their gravitational influence. The third process is the slow gravitational evaporation of galactic structures, the process by which stellar remnants exchange energy in close encounters and gradually separate, with some being flung outward to intergalactic space, and others being driven inward toward the central black hole. Fred Adams and Gregory Laughlin estimate that this process takes roughly 10 to the 19th to 10 to the 20th years to complete for a typical galaxy. This is far beyond 10 trillion years. The galactic evaporation is just beginning at 10 trillion years. The fourth process is the one that physicists most fiercely debate in the context of the Voyager's ultimate fate: proton decay. We named this process in the previous section, and we need to return to it now with sharper attention, because it determines whether there is any version of the Voyagers that persists into the universe's truly deep future, or whether they dissolve long before. Most grand unified theories predict proton lifetimes of around 10 to the 32nd to 10 to the 36th years. Some supersymmetric theories predict even longer lifetimes, extending to 10 to the 40th years or beyond. If the proton is stable, none of this applies. The Voyagers persist indefinitely as far as atomic physics is concerned, slowly accumulating damage from cosmic ray impacts, slowly having their surfaces pitted by interstellar dust encounters, but fundamentally intact in their atomic structure. We genuinely do not know which scenario is correct. The Super Kamiokande detector in Japan, buried under 1,000 meters of rock beneath Mount Ikeno, has been searching for proton decay since 1996. It has not found it. This constrains but does not eliminate the possibility. It simply means that if protons do decay, their lifetime is longer than current experiments can probe. As physicist and cosmologist Fred Adams has noted, the uncertainty about proton stability is one of the most consequential unknowns in the long-term picture of the universe's future. Set the uncertainty aside for a moment and follow both branches. If protons are stable, the Voyagers drift forward through the degenerate era, through the slow evaporation of the galactic remnant, through the billions upon billions of years as white dwarfs cool into black dwarfs and black holes dominate the gravitational landscape, and into the era of black hole evaporation. Black holes, as physicist Stephen Hawking proposed in 1974, are not permanent. They slowly emit thermal radiation, now called Hawking radiation, through a quantum mechanical process at the event horizon. The rate of emission is inversely proportional to the black hole's mass. Smaller black holes evaporate faster. For a stellar mass black hole of perhaps 10 solar masses, the evaporation timescale is roughly 10 to the 70th years. For the supermassive black hole at the center of Milkomeda, which by the time of the merger will have a mass of perhaps several 100 million solar masses, the evaporation timescale stretches to roughly 10 to the 92nd power years or so, still almost incomprehensibly longer than anything discussed so far, but short of the 10 to the 100th year timescale reserved for the very largest possible black holes. 10 to the 99th years. This is a number so large that writing it out would require 100 digits. The entire history of the universe to date, 13.8 billion years, is 10 to the 10th power years. The ratio of the supermassive black hole's evaporation time to the current age of the universe is roughly 10 to 89. The universe has less than 1/10 to the 89th of its eventual lifespan behind it, if we measure life as lasting until the last black hole evaporates. Against this backdrop, 10 trillion years, the timescale we have been asked to explore, is the opening heartbeat of a journey whose true end is an almost inconceivable distance away. If protons are not stable, the picture is different. The Voyager spacecraft, built from atoms, begin to slowly dissolve at around 10 to the 34th years as individual protons convert to lighter particles. The aluminum frame softens, not dramatically, not quickly, but over the vast stretches of proton decay timescale, it gradually loses its structural integrity. The copper of the golden record follows the same path. The gold plating, also composed of atoms with protons in their nuclei, follows as well. By roughly 10 to the 35th or 36th years, essentially no macroscopic solid objects remain in the universe if protons decay. The matter that composed the Voyagers has been converted into a diffuse cloud of electrons, positrons, neutrinos, and photons, spreading outward into an already unimaginably dilute universe. But here is the crucial point. 10 trillion years sits at 10 to the 13th power years. Proton decay begins at 10 to the 32nd to 34th years at the earliest. The Voyagers are safe from proton decay at the timescale we are exploring. At 10 trillion years, on either branch of the proton stability question, the Voyagers are intact. The spacecraft are intact. The records are intact. The atoms are intact. The information is intact. Somewhere in the dim, cooling remnant of Milkomeda, or possibly in the intergalactic void beyond it, two machines built by human hands in the 1970s are still traveling. They are cold. They are dark. They are silent. They have been silent for almost as long as the current age of the universe, multiplied by 725. Every star that was alive when they launched has died. Every planet that circled every star in the galaxy has been scattered or consumed. The Sun is a black dwarf, or is approaching that state. The Earth is gone, either consumed by the Sun's red giant phase, or scattered into the dark when the Sun's mass loss sent it drifting outward and then released it into the galactic night. And the Voyagers are still there. This is the reframing that changes everything we have looked at so far. We have been treating the Voyagers as a chapter in the history of human spaceflight. We have been thinking about them as the culmination of the Grand Tour mission, as the product of Gary Flandreau's 1964 calculation, as the machines that photographed Io's volcanoes and Neptune's storms, as the first human-made objects to cross the heliopause. And they are all of those things. But at the time scale of 10 trillion years, they are something else entirely. They are the most enduring physical record of human civilization's existence. Not the pyramids at Gliese, which will have eroded to dust within a few million years. Not the underground archives we have buried, which will be consumed when the sun expands. Not the radio signals we have been broadcasting since the early 20th century, which are dispersing outward as an ever-thinning sphere of electromagnetic noise, becoming indistinguishable from cosmic background radiation within a few thousand light years. Those radio signals are not durable records. They are an expanding whisper, growing quieter with every passing year. The Voyagers are different. They are physical objects. They carry information in a physical medium, and they are moving away from everything that could destroy them. There will be one more profound transformation of the universe after 10 trillion years, one that touches directly on the Voyager's fate. And it is the transformation that philosopher and cosmologist Carl Sagan gestured at when he designed the Golden Record, with such obvious awareness of the yawning scale of time. It is the transformation that makes the record not merely a scientific artifact, but a philosophical statement about what it means to exist briefly in a universe that will persist almost forever. But before that transformation, there is one more thing to look at in the universe at 10 trillion years. the question of what the sky looks like from wherever the Voyagers are. The sky, if there were eyes to see it, is dark, almost entirely dark. The white dwarfs, still faintly warm at this early stage of the degenerate era, would appear as extremely dim, reddish points of infrared radiation. They would not be visible to human eyes. There are no human eyes. But to any instrument sensitive to long-wavelength infrared, the remnants of Milkomeda would appear as a sparse fog of dim, cooling objects, none of them remotely as bright as the sun was, none of them producing the kind of optical light that painted the Milky Way's spiral arms in the photographs taken from Earth in the brief era of human civilization. Occasionally, in this dark future, there is a flash. When two stellar remnants collide, or when a white dwarf accretes enough material from a companion to exceed the Chandrasekhar mass limit and collapse, there is a supernova. These events, which in the Stelliferous Era were common enough to be detected in distant galaxies by human astronomers, are now extraordinarily rare. The Voyagers will be drifting through what would be a completely unrecognizable galaxy, in the description offered by researcher Charles Oberg, where the only source of significant illumination will be supernovas that result from the once-in-a-trillion-year collision between these stellar remnants that still populate the galaxy. Our work, found on the records, may bear witness to these isolated flashes in the dark. That sentence, written by Oberg about the golden records, has a quality that resists paraphrase. It acknowledges that the records are not merely a scientific artifact, or a diplomatic gesture, or a technological achievement. They are testimony. They are the testimony of a civilization that existed in a particular moment of cosmic time, when stars were burning and oceans were moving, and creatures built machines and aimed them at the dark and put their music inside. The flash of a once-in-a-trillion-year supernova illuminates briefly the surface of two spacecraft drifting in the cold. The records catch the light passes, the darkness returns. The journey continues. 10 trillion years is a specific answer to a specific question, and having arrived at it, having traced the path from Cape Canaveral in September 1977 to the dim, cooling remnant of a merged galaxy in a universe populated mostly by darkness and slowly cooling stellar corpses, it is worth stopping here before the final descent into philosophy, not to rest, to look back. The journey began with a graduate student named Gary Flandreau in 1964, noticing an alignment in orbital mechanics that nobody had quite assembled before. It continued with 2 launches from Cape Canaveral in the summer and autumn of 1977. It passed through the volcanoes of Io and the rings of Saturn and the nitrogen geysers of Triton. It crossed the heliopause in 2012 and 2018. It moved through the Oort Cloud over tens of thousands of years. It passed through the gravitational neighborhoods of Gliese, 445, and Ross, 248, and Sirius without being captured by any of them. It witnessed, from an ever-increasing distance, the expansion of the Sun into a red giant. It drifted through the gravitational chaos of the Milky Way's merger with Andromeda. It survived the end of the Stelliferous Era, when the last red dwarf went dark somewhere around 100 trillion years from now, well beyond our specific 10 trillion year mark. And at 10 trillion years, it is still there, still moving, still carrying its records, in a universe that has grown cold and dark and vast beyond any frame of reference that existed when the spacecraft was built. That is the arc. And the Ark contains a question that has been building since the very beginning, a question that physics alone cannot answer. What does it mean? Not in the technical sense. The technical sense has been well served by everything we have covered. In the technical sense, the Voyagers are objects in motion subject to Newton's laws and gravitational perturbations and the long-term thermodynamics of a cooling universe. In the technical sense, their story is completely described by the equations that govern their launch and continue to govern their drift. But the technical description leaves something out. It leaves out the fact that human hands built these machines. It leaves out the fact that Carl Sagan sat in a committee room at Cornell University and argued about which piece of music best represented the joy of being alive on Earth. It leaves out the fact that the greetings recorded in 55 languages were spoken by real people with real voices who knew they were speaking into a void that might never answer. It leaves out the fact that somewhere in the degenerate era, 10 trillion years from now, the sound of a mother speaking to her newborn child is still encoded in the grooves of a gold-plated disc attached to a machine traveling at 17 kilometers per second through a darkness that has swallowed every star. The technical description leaves out the human being, and the human being is the point. There is a way of looking at the Voyager mission that makes it about technology. There is a way of looking at it that makes it about planetary science. There is a way of looking at it that makes it about the Cold War politics that funded it, and the budget battles that nearly killed it, and the engineering triumphs that saved it when computers failed and gyroscopes degraded and memory chips corrupted. All of those framings are accurate. None of them is complete. The complete framing requires acknowledging that what Gary Flandreau saw in 1964 was not only a trajectory, it was a door that opened once every 175 years and would not open again in any living human lifetime after 1977. And what the people of NASA's Jet Propulsion Laboratory did was walk through that door, carrying everything they knew and everything they hoped, and send it outward into a universe that did not ask for it and may never know it was sent. That is the existential fact at the core of the Voyager story. We sent them because we could. We sent them because the window was open. We sent them because something in human nature, something that builds pyramids and cathedrals and particle accelerators and ocean crossing ships, refuses to sit still when there is somewhere to go. We sent them into a future we could not see, toward destinations we had not chosen, carrying a record we had almost no reason to believe would ever be found. And we put music on the record. This is the detail that refuses to be merely technical. The scientific instruments on board the Voyagers were chosen for specific measurement tasks. The cameras were chosen to photograph specific objects. The magnetometers were chosen to measure specific fields. But the golden record was chosen to say something that no instrument can measure and no equation can describe. That we were here, that we found the universe beautiful, that we wanted to share it with whatever or whoever might one day exist in the same darkness we were reaching into. The closest historical parallel is not another space mission. It is the practice, common in many ancient civilizations, of burying the dead with objects of value. Not for the dead, who no longer needed those objects, but as a statement directed at whatever lay on the other side of the boundary between the living and the unknown, The Egyptians built pyramids that they knew would outlast their civilization, that they built anyway, because the scale of what they were commemorating demanded a scale of response. The builders of Stonehenge arranged massive stones in precise geometric patterns with no written record of their purpose, driven by something that looks, across 4,000 years, very much like the same impulse that put whale songs on a gold-plated disc in 1977. We are a species that reaches toward permanence, even as we are surrounded by impermanence. Every civilization that has ever existed has confronted its own mortality, not just the mortality of individual people, but the mortality of the civilization itself. The knowledge that the language you speak will be forgotten. The knowledge that the gods you worship will be replaced. The knowledge that the walls of your city will fall and be covered by soil and be excavated by people who cannot read your writing. The ancient Sumerians knew this. The Greeks knew this. The Romans knew it explicitly, and some of their most beautiful writing is about the persistence of beauty in the face of time's erasure. What is different about the Voyagers is the scale. The pyramids will be gone in tens of millions of years, eroded by the slow, patient work of wind and rain and the shifting of tectonic plates. The languages on the Golden Record include Sumerian, which was already ancient when the pyramids were young, and which is now spoken by no living person, understood only by specialists who have devoted their lives to its study. The music on the record includes pieces written by composers who have been dead for centuries. The photographs include images of a planet whose oceans will evaporate in 1 billion years. All of it will be gone, except the record. The record will still be there, not playing, not readable by any instrument we know will survive, not findable by any civilization we know exists. But there, the grooves will still hold the information. The gold plating will still protect the copper beneath. The spacecraft will still carry it forward through a universe that has outlasted everything else humanity ever built or said or believed. This is the thought that researcher Charles Oberg arrived at in his work on the long-term fate of the Golden Records. The records may bear witness to the last flashes of light in an otherwise dark universe. Witness. The word is precise. A witness does not change what it observes. It simply persists long enough to be present. The Golden Records are witnesses to the Stelliferous Era, to the brief, improbable window in cosmic time when stars burned and planets circled them, and at least one of those planets produced creatures who looked up at the burning stars and felt something that made them want to respond. That window is closing. At 10 trillion years, the window has been closed for a very long time. The last red dwarf went dark roughly 90 trillion years before the 10 trillion year mark of our story, which is to say that if 10 trillion years is now, the last star died 900 billion years before our now. The stars died before 10 trillion years, not after. We set our specific marker at 10 trillion years because that is the question posed at the beginning of this journey. But the stars were already gone. The universe is already deep in its long, cold, dark Middle Age. The Voyagers have been traveling through darkness for longer than the universe has been alive. Sit with that sentence. They have been traveling through the degenerate era, the era of no new stars and no fusion and no starlight, for longer than the entire previous history of the universe from the Big Bang to the present moment. They are in the part of the story that makes everything before it look like a prologue. And they are still moving. Something about this refuses easy comfort. It is beautiful, genuinely, strangely beautiful, the way extreme mathematics can be beautiful, the way an equation that describes something vast and true carries its own kind of aesthetic weight. But it is also heavy in a way that beauty alone cannot account for. The heaviness comes from impermanence. We know from physics that even this is not the end. The Voyagers will continue beyond 10 trillion years if protons are stable, drifting through the black hole era, watching from a vast distance as the last supermassive black holes evaporate through Hawking radiation on timescales that dwarf the current mark by factors of tens of trillions. They may persist in some form as long as ordinary matter itself persists. And if protons are not stable, they dissolve eventually into the lightest particles the universe contains, spreading outward until nothing of the original structure remains. Either way, the information on the golden record is not permanent. Either way, the instruments are not permanent. Either way, the aluminum and titanium and copper and gold that compose these spacecraft are temporary residents of a universe that will eventually reduce all complexity to maximum entropy, all structure to uniform diffusion, all information to noise. Fred Adams and Gregory Laughlin concluded their 1997 survey of the universe's future with a statement that has the quality of an epitaph. The universe will expand forever, becoming increasingly dark energy dominated, while the temperature and matter density asymptotically approach zero. Not quite zero, approaching zero. A universe in which the approach to emptiness is eternal, but never quite completed, in which the last vestiges of structure persist longer and longer, but the gaps between them grow wider and wider, and the cold grows deeper and deeper without ever quite reaching the absolute zero that would mark the true end. The Voyagers drift in that endless approach. They are not the last objects. They are not special in any physical sense among the cooling white dwarfs and neutron stars and black holes that share their environment. They are small. They are built from ordinary matter. They have no unique physical properties that distinguish them from any other piece of processed metal in the universe. What distinguishes them is not physical, it is intentional. They were sent, deliberately, by beings who knew they were sending them, who chose what to put on them, who argued about which music was most worth preserving, who decided that the sound of the ocean and the call of a bird and the opening of Bach's Brandenburg Concerto were the things that best said, "This is what we were." The distinction is intentionality. The universe is full of objects in motion. Asteroids travel through the interstellar medium. Rogue planets drift without stars. Stellar remnants coast through the dark after their galaxies evaporate. None of them carries a message. None of them is trying to say anything. They are matter following the laws of physics, nothing more. The Voyagers are matter following the laws of physics, and also something more. They are matters that were given a direction and a purpose by minds that understood what they were doing and did it anyway. That is the distinction that 10 trillion years of travel does not erase. The purpose persists in the object, even when the minds that created the purpose are long gone. This is perhaps the deepest truth the Voyager story contains. The universe does not require purpose. It operates without purpose through the impersonal application of mathematical laws, without preference for any outcome over any other. Stars form and die, not because they mean to, not because their formation serves any goal. The universe expands, not because it intends to, but because the initial conditions of the Big Bang set it in motion, and dark energy maintains that motion. The laws are real and consistent and beautiful, but they carry no intention. Into this purposeless vastness, in the late summer of 1977, human beings inserted two small objects that carried intention with them. Not permanently, not forever, but for a span of time so vast that it includes the death of stars and the merger of galaxies and the long cooling of the universe into its dark middle age. For that span of time, which includes every moment we will ever live, and every moment our descendants will ever live, and every moment any living thing on Earth will ever experience, the Voyagers are out there, still moving, still carrying their records, still aimed at whatever the galaxy places in their path. If this has changed how you think about these spacecraft, about this mission, about what it means to build something and send it outward into a universe that does not need it, then the time spent in this telling was well spent. There is one last thing to say, and it does not belong to physics or cosmology or the mathematics of proton decay. It belongs to the moment in 1977 when Carl Sagan held the finished golden record and understood, with the full clarity of his scientific training and the full depth of his humane imagination, that he was holding something that would almost certainly outlast every other human artifact ever made. He chose not to be paralyzed by the improbability of it all. He chose instead to make the record as worthy as possible of whatever vast and unforeseeable future it was heading into. That choice, made once by one person, in one room, in one moment, is now encoded into the physical structure of two machines traveling at 17 and 15 kilometers per second through a universe that has outlasted everything else he ever touched. The sun rises and sets over a planet that will eventually be swallowed by its own star. The languages of the golden record are spoken by mouths that will not exist in 1 billion years. The civilizations that built the instruments Voyager carried have changed beyond recognition in the 50 years since launch, and will change beyond recognition again and again and again before the last red dwarf goes dark. And the spacecraft travel on. They traveled before any of us were born. They will travel after every trace of us is gone. They carry the best of what we knew how to say in the brief moment we had to say it, aimed outward into a darkness that is patient enough to outlast everything except the act of sending them. If you carried this journey with you from its beginning, from the gravity assists and the Jovian volcanoes and the icy rings of Saturn, through the crossing of the heliopause and the long passage through the Oort Cloud, through the stellar close approaches and the galactic orbits and the merger with Andromeda, through the Stelliferous Era's end and the arrival at the dim, cold, vast universe of 10 trillion years, then you have done something the Voyagers themselves cannot do. You have understood it. The spacecraft travel but do not know. They carry music but cannot hear it. They hold a record of human joy and grief and curiosity and reach, but they feel none of those things. The feeling belongs to you. The understanding belongs to you. The weight of those 10 trillion years lands in a human mind, or it lands nowhere at all. It landed here tonight. In the dark, in the quiet, in the particular hour when the world outside has slowed, and the ordinary noise of daily life has softened into something that allows a question like this one. A question about where 2 aluminum spacecraft will be in 10 trillion years to feel like the right question to be asking. It is the right question. Not because of what it tells us about spacecraft, but because of what it tells us about time and scale, and the astonishing accident of being the kind of creature that can ask it. Before we close, the full arc of what we covered tonight deserves its moment of recognition. Gary Flandreau's 1964 insight that opened the window for the Grand Tour. The twin launched from Cape Canaveral in 1977. The discoveries at Jupiter and Saturn and Uranus and Neptune that gave the spacecraft their final irreversible velocities. The crossing of the heliopause, first by Voyager 1 in 2012, then by Voyager 2 in 2018. The long, silent passage through the Oort Cloud over tens of thousands of years. The close approach to Gliese 445 in 40,000 years, and to Ross 248 at roughly the same time. The galactic orbit, 225 million years per revolution, borrowed from the Sun's own motion around the Milky Way's center. The merger with Andromeda, 4 to 5 billion years from now, scattering the Voyagers into new and less predictable orbits. The end of the Stelliferous Era around 100 trillion years from now, when the last red dwarf goes dark and the universe enters the degenerate era. The cold, dim universe at our 10 trillion year marker, where two spacecraft built from ordinary matter drift through a darkness populated by cooling stellar remnants and the slowly evaporating black holes that are all that remains of the galaxies that once blazed with the light of hundreds of billions of stars. And on each spacecraft side, a record, intact, silent, carrying everything we chose to say. The Voyagers are our message in a bottle, thrown into an ocean so large that the word ocean has no meaning, toward shores so distant that the concept of shores dissolves entirely. We threw them anyway. That is who we are. If this changed how you think about these two spacecraft, about the civilization that built them, about the universe they are crossing, then the time was well spent. Thank you for making the journey.